All right, welcome everybody. Today I'll be talking about the CyaX-Sharp loader, which is a reference, of course, to C# in this case for the title. For the table of contents for today, it's quite filled. First, I'll talk a bit about who am I, who's giving this presentation, and then I'll talk a bit about the more generic terms. What are loaders? I'll talk a bit about the egg and onion model that is probably known to quite some of you. I'll be talking about loaders and their coverage in blogs in general, the attribution of this loader from multiple angles. I'll talk a bit about confusing family names, as this loader is known by multiple nicknames, which might be confusing because you might know one but not the other, or vice versa. I'll talk about the capabilities of the loader itself, so what can it do technically, and I'll be talking about the extraction of both the payload and the loader's configuration for a single loader, but also in bulk. And then the outcome of the bulk analysis that I did. And in the end, I have a conclusion to tie it all back together. So first of all, who am I? Well, my name is Kersten. I go by the nickname of Libra or Libra Analysis on Twitter. And currently I'm working for McAfee's advanced threat research team. In my spare time, I write blogs, although also for work. I wrote my own binary analysis course, which people can use to get into reverse engineering and analyzing malware. I write software as well. Last year, I gave a presentation here at the Confidence Conference about Android Project Creator, which is a tool you can use to analyze APKs. So that's how I spend my time, basically. But moving on to this topic, what are loaders? So really briefly, a loader is used to load, as its name already indicates, a remote payload or a payload that's embedded within the file. So it can be either or both. And it can have additional defensive measures. So it might be checking if it's running in a sandbox, in a virtual machine, if antivirus is installed, and it might abort the execution or perform other measures once these parts are encountered. And now these payloads that are within these loaders, they are generally encrypted and or obfuscated because otherwise it wouldn't make too much sense to use a loader. If you have a YARA rule for a specific family, let's say Agent Tesla, because that will become relevant later on in this talk, the rule will match the family that you're looking for. However, if I were to put Agent Tesla in a loader, then your YARA rule would not catch the loader as dropping Agent Tesla. However, it would obviously be working if you have a YARA rule to detect this loader, but then you still don't know what the payload family is. So there's a distinction in there. And the loaders can also be linked together. So you can have one loader that loads the next, and so forth and so forth. Although there's a point where it doesn't really add anything to link more. But some people are really creative. In this research, I encountered at least one sample that was in a chain of 14 loaders, nearly identical ones as well. So some people really see a benefit, whereas others just try to bypass the default security measures that a lot of companies have, or at least should have. Then the egg and the onion model. So like I said, loaders are used to get a payload on a target, be it once, be it multiple times, either works. But in this case, you want your company to have a network structure more like an onion rather than an egg. So the egg has a really hard outer shell, which is nice. You know, once you get out and you're baking a cake, you just need to crack the egg, put the inside of the egg in the basket, and you can continue. However, once an attacker is inside a network that has a really difficult perimeter to breach, it's all fair game if there is nothing else in there. However, with the onion approach, for every step along the way, the attacker needs to have more effort, and there's a higher chance of catching the attacker because we're all humans and we all make mistakes eventually. So maybe it's not in the first layer, maybe it's not in the second layer, but if you need to struggle for every step of the way, chances are that you will be catching the attacker much earlier on. And this also goes for the chain of execution for malware. So we have the really common ones where you have a Word macro or an Office macro that then launches some PowerShell script, it downloads something, it executes it. And then generally that's a loader that's fetched. And then the loader might deploy the eventual malware itself. So if you were to be able to avoid the first step, but also the second and the third and the fourth, then you would be as safe as possible. However, if your main focus is just on disabling the first step, then the moment the first step changes, or for some reason it didn't get blocked by the antivirus you're using, then you have no insight anymore. So that's something that I want to reflect on here, as the coverage of loaders in blogs is quite often neglected or omitted. And research is meant to be reproducible. So if you have a loader within the chain of events, then quite often it's only a small remark within the research paper, i.e. after unpacking the malware, we found this and this. Although that is great and the sharing is appreciated, it's also really useful for other researchers, for other people in the industry to know how to do this. But then again, the absence in these reports is also understandable. You have a limited scope to write about, you have limited time to do so, and the reuse of loaders for different families might also be repeating information in blogs. So that was one of the drives for me to write about this loader, because I wanted to shed some light on it. I'm moving on to the attribution of this loader. The firm 360 Total Security links the loader to a threat actor dubbed Vendetta. During the research, there has been at least one leaked loader that I encountered. So that makes it really difficult for me, at least, to state who is using it or who is behind it. And based on the public reports of this malware that we encountered, the sectors have been really varying, as well as the geographic locations where the malware has been observed, making the attribution from our side difficult to say the very least. So for now, we're not attributing this to any specific group. It's more providing insight in how the malware works. So, like I started the talk out, the CyaX-Sharp loader, as we refer to it, has multiple names. The other common name for it is the ReZero loader, and in some cases also Lazarus, but this is not to be confused with the APT. This is, well, surely distinct. There's a great blog by GData's Kersten, who sheds light on ambiguous naming schemes for malware, and also provides several potential solutions what we as an industry can do. But I found it interesting to see that the names that were used were different, even though the ReZero has a higher share, so to say, based on the total amount of samples. 42%, it's rather big compared to the much lesser used 18% of CyaX-Sharp. So logically, it would follow that if something is, nearly half of the samples that I encountered were named ReZero, it would make more sense to come up with that name as a default name. So why isn't it? Well, if we look at the first seen date on VirusTotal, as is plotted on the horizontal axis, then we can see that the ReZero samples with the name ReZero only started emerging from February last year onwards. However, the CyaX-Sharp name has been used quite a bit prior to that already in July 2019. So the first occurrence here is probably what named the malware rather than the most frequent name. But looking back, it might be an easy conclusion to jump to state that re0 would be the official name to refer to. So this is more of a historical point of view to it. So I've talked quite a lot about what is a loader, what does it do in general, but what does this loader do? Well, in this case, it first starts by decrypting the embedded payload, if there is any, in memory, and parsing its configuration file internally. Then the main function is called, and from then onwards, it also depends on what the configuration file said when looking into the functions that it has. So the dotted line indicates that it is potentially doing this, whereas the solid line means that this is done for sure. So the first few steps are always executed, and then it depends on the version and also the configuration itself on what is performed in terms of actions. So it can disable Defender. I've seen some samples, but not enough to say it's a trend, rather an edited version of sorts that disable different antivirus suites. But Defender was embedded as a proper option. A delay in execution using sleep to just wait X amount of seconds. A message box can be displayed to the user with a fake error message. The detection for both virtual environments and sandbox is possible, and the execution of a remote payload, the persistence as a scheduled task, and the execution of the embedded payload. Note that the option to execute a remote payload and launch the embedded payload are combinable for the actor. So you can have a remote payload that you launch only to launch your embedded payload afterwards. You can do this for a variety of reasons. Maybe you have a special implant you want to drop, or you want to have different malware on the machine, or you want to have a different goal. You can do that in here, but you can also obviously use your embedded payload to launch something that would be up to the attacker's tactics, techniques, and procedures in that case. So how does this look in code? Well, they were nice enough to at least once use a version with very little obfuscation, little to none, and include some helpful symbols along the way. So this is the main class with an excerpt of some fields that are in there. So you can see a string, which is a password. You can see a byte array, which is the payload. So this is the embedded payload, which is loaded from a resource. Then some sort of decryption is done, and then some unscrambling is done, only to result in the decrypted payload. Then there's a string called K, which has some numeric values in there with a lot of pipes in between. We can see that the string array below splits the given string into a string array based on 2 pipes. So the string AA, or the string array AA, is the config array. In this case, it's not necessarily a file. And you can see in the 2 fields below that are included in the screenshot that based on the value on a specific index of this array, specific values are triggered within the malware. So how does this look like within the main function, right? Because so far in the previous slide, I explained that first the program is started, the payload is decrypted, the config is set, and then we end up in a main function. So you can see here that there are, as dnspy conveniently named flags. And we can see that, for example, flag 2 is a Boolean, which is true if the anti-emulation value based on the configuration is equal to 1. And if this is true, then Windows Defender is disabled. And then we have more and more of these options for anti-virtual machines. We have anti-sandboxes. So we have a lot of options here to potentially go into or skip. And we can also conveniently see that in case of the detection of a virtual machine, as the function returns a Boolean if this is true, the program simply exits with the status code 0, which indicates a normal ending. So how is the defender tool disabled? Basically by changing some registry settings on the computer and assuming that you have a specific identity on the computer, because you need certain permissions to do this. So both the anti-sandboxing and the anti-virtual machine functions are rather lengthy. I just put like the first few lines of each, as they kind of reflect the sentiment. So the anti-virtual machine checks for the hardware that VirtualBox delivers to your computer, which is obviously software that you need for that. And it does so for a lot of different vendors and other tools that you generally encounter on virtual machines and not on a normal machine. In case any of these checks returns is present, it returns true. And as we saw in the previous screenshot, the program exits. And the same goes for the anti-sandbox. It checks for modules, it checks for names, files, you name it. And there's quite some in there. So that's how that's done within the loader. Moving on within the main function, we can see here that it can download something, and based on the configs link and file name, this file is downloaded and then executed. We can also see that it can persist using the startup. We have two different versions of the payload execution. In the bottom, we see flag 10 and flag 11, where we have reflection and the start of the injection. But first, I want to talk a bit about the startup. And the startup or persistence is done via the scheduled tasks. And this is actually what led me to find over 500 different versions of this loader in a variety of platforms online, because they have a template that they load based on the scheduled tasks or how you should submit one. And they only replace the name and the file name within. But there's a very specific way that this template looks like. As you can see, the square brackets with location and user ID are within the resource. And if you were to run strings on such a binary, you could actually view the full resource. Now, the point here is that if you were to obfuscate a sample, then you will not be able to view it if you were to use Confuser X, for example, depending on the settings. But if done properly, the resource itself is not really human readable anymore. So you would, in some cases, need some deobfuscation prior to running a Yara rule that matches this. But still, it's an interesting way to find one linking pin for all samples. And the date on which the scheduled task is allegedly first installed is very specific and from 2014, which is also interesting if you look at the scheduled tasks on your machine. Moving on to the execution, the reflection is loading a different .NET binary, and it needs to be .NET binary for this to work, after which the entry point of the file is invoked, potentially with an empty string, with an empty string array, but if need be, and otherwise without. If anything goes wrong here, meaning if the binary is not based on the .NET framework, or for any other reason, anything goes wrong, it moves to the start inject. And this is also the other way of launching the payload. This is a process hollowing function using the interoperability service of .NET, meaning it can use native system calls and native information along with the help of certain structures that you need. And then it performs the normal way of process hollowing a target. The target itself is based upon the config itself. So there are multiple options in here. all based on either binaries that are present on Windows or the loader itself. But I'll get back to that later on. The class itself, based on the code similarity, we trace that back to the run PE class of nixcat on GitHub. Even though the compiled code looks slightly different on the right than it does when you look at the GitHub version on the left, we can clearly see the for loop, which tries 5 times to start the sample. And if you look on the right side, we can see the bro.handle run, which is the following itself, is executed 5 times maximum. And otherwise, it basically fails based on the, well, it's a bit obscure, but based on the go-to and the returns there. So we, based on the code similarity, we assume that the public source code here has been used, but this is no indication or provides no information on the fact that this actor would be tied to this loader. We have no evidence for such a claim, but just to avoid speculation, I want to mention that. So the loader itself, like a lot of malware, changed over time. And what we mostly have seen is that the configurations array size has increased. So in the graph below, you can see that config 29, config 37, and config 38 are blue, orange, and gray respectively. And we can also see clearly how one version died out and the next one was used. Be it that some samples, for example, in December 2020, we can still see some samples of config 29, but the majority of its usage was way before that. So these new fields within the array also provide options for new functionalities that they added. So in the screenshot I shared early on, the sleep was always present in between 45 and 60 seconds based on random value between those. However, in later versions, the sleep functionality is configurable, both to turn it on and off, but also to configure a set length that you as an actor want. And a custom message box prompt can be shown to a user, be it with whatever message and in whatever style you want. So it can be yes, no, with a warning, or it can be only an okay dialogue. So there's some freedom there as well. So the collection of the 513 unique samples based on the Yara rule has been completed for this thought experiment, so to say. So how do we then continue and talk about the fact that we want to extract the payload and the configuration array for each of these samples without doing it manually, obviously. Even though 513 is a lot of work, it can still be done manually. But ideally, you want to work on something and have a tool that does this for you, so you can further automate the process. Let's say a Yara rule fetches or catches this loader, then you might want to refer to your extraction tool and say, okay, well, check what it does and give me the payload, and then we can run the payload again through the Yara rules to see if we maybe have a hit on this. And then it also doesn't matter if you were to chain this loader multiple times, because you can keep this doing iteratively. So the plan of approach is pretty straightforward. We want to obtain the payload and the configuration array. We want to decrypt the payload and we want to dump it to the disk because we want a copy of it, and want to parse the configuration in basically any form that we want to use. But as a main caveat here, avoid resetting the machine you're doing the analysis on, because that would make the analysis a lot slower. But it's not necessarily a hard requirement, but it was one for me when I worked on this, because I figured it should be doable. So how do we go ahead? Well, we can use the reflection related classes that the .NET framework provides. And obviously you need an IDE of sorts, where I used Visual Studio. So classically and generally, what you want to do is you want to recreate the decryption routine. You want to fetch the resource, you want to decrypt it, and then you want to go ahead with whatever you want to do with it. But there are downsides here. So it would require continuous maintenance, simply due to the fact that a single change in the decryption routine would break your tool, which is kind of a downside. But in some cases, there's no other way around it. However, what you can also do is get lucky. You can find a flaw. And in this case, static variables really prove their worth. So just digging in on static variables, as you can see in this screenshot that I showed you earlier, the variables are all static. So what does this mean and why is this useful? Well, per Microsoft's documentation, in the quote that I have, it says the type information for a static class is loaded by the .NET runtime when the program that references the class is loaded. It is guaranteed to be loaded and to have its fields initialized and its static constructor called before the class is referenced for the first time in your program. So essentially, if I were to load reflectively a tool or one of the loader instances, like a file, it would initialize all these static variables. Now, in this case, we can see that both the declaration of the variable payload, but also the initialization is done at once, because we can see that payload equals extra.unscramble, yada, yada, yada. So essentially, once we load the file in memory, this code is executed, and we can simply fetch the payload in raw form from memory. Thereby, we do not care if the XOR decryption changes, if the unscramble changes, or if they find a completely new way of decrypting it, as long as they keep it statically like this. Now, note here is that it's a private field, but for that we don't really care too much, as you will see in a bit. So obfuscation becomes irrelevant for this piece. Obviously, if you were to analyze it manually or look at it or want to find differences between versions, it will become relevant again. But the fields are assigned their value prior to being accessed. And if you have Confuser X, for example, enjoys static constructors, which then assigns the value, these are also executed prior to the access that we want. So the new plan of approach is even simpler. We simply want to load it, and then we want to find and handle the required fields within the binary. Now there's an asterisk here next to the load part, because there are different ways of loading it. You can load it for reflection only, you can fully load it. But in this case, I just use the assembly.load after getting the binary as a byte array. But well, feel free to change some stuff there if you want. And you do need some settings in your Visual Studio project as well, as you need to allow untrusted code from external sources, because that's what you're doing, otherwise it cannot execute. This talk will cover the main concepts briefly, but the link here covers a complete write-up on how to make such a extractor. So this is a really shortened version of the extraction class. So basically, you provide the path to a file to this function. You then create an assembly object using assembly.loadFile. And then you just iterate over all the types within that file. So basically, these are the classes. Now, then we want to get the fields from each class. We want to get the fields that are non-public, i.e. private, and we want to get all fields that are static. So we get all these back, and then we simply iterate over them. So we want to get their value and per field, and we want to check the type. So if the value is a string array, then it might get interesting. And if the value is a byte array, it might also get interesting. Now, take in mind that simply checking the type is not necessarily a good idea to only do that, mainly because there can be multiple string arrays within the binary and also multiple byte arrays. So in this case, I added a check to check if the length is more than 28. And given that it's quite sizable, you can fairly safely assume that this is indeed the config array that we're talking about. And in this case, some values are printed. Obviously, there's a lot more to it, but then you would either have font size 0 in the screenshot, or we would have tons of screenshots, hence the write-up. And for the byte array, there's a check for the first and second byte, basically for the PE header. So if it's a PE file, we write it back to the path that was originally given, but we append _extract it to the newly created file. So based on this, we have all the data, we have the config, and we have the payload. We can then continue with the poke analysis. So given that the YARA is on VT, or at least VT links it to the ETR repository, if you were to find this one on VibesTotal, you actually do get a notification. And the rule itself is also publicly available if you want to use it in in-house scanning or for different research. So all figures I'll be talking about are about the 513 loaders. So if you see percentages, that's what it's based on, unless specified otherwise. Now, the execution method has several options. You can hollow MS build, you can hollow VDC, you can hollow the reg service, you can hollow the loader, and you can do a direct launch. Now, 72% of all loaders hollows the loader, or a new instance of the loader, technically that is. But only 10% goes for a direct launch of the payload. Having said that, the direct launch in old versions is basically still process hollowing because it launches a second embedded payload, which is only there to perform process hollowing. So the 10% is potentially even less, but at least 10%. The scheduled tasks are interesting as well to see because roughly half, or 54%, of the loaders used persistence, whereas the roughly other half didn't. But take in mind here that the fact that since loaders are often linked or chained, so to say, and the frequency of the CyaX-Sharp loader is probably higher than the 500 or so samples I encountered, as these hits were only first in line. So if you do a retro hunt, for example, then it doesn't check what else is executed in memory. So if there's a different loader prior to it, then you won't find it. So other loaders can provide persistence for malware samples. Some malware samples don't care about persistence. And in other cases, the final payload itself actually has a persistence mechanism built in on its own, meaning that no loader is required to do so. So it's interesting to see that half of it used it, but it doesn't mean that only half of the payloads persist itself on the target. And then talking about sleep or delayed execution, if you will. So only a small percentage of the loaders actually used sleep, about 23%. But what was interesting to see is that the sleep time itself is roughly based around what humans see as round numbers. So you can see that there's 5, 10, 15, 30, 45. Those are small peaks in terms of how many seconds sleep should be used, or the sample should sleep for that length. And you can also see that 60, 66, and 600 are also normal for humans because you just press 6 2 times rather than 60. But it's an interesting perspective to see what preference there is among actors. But even a few seconds sleep will not matter too much once on the system from a defensive point of view. However, it might help with other forms of detection evasion. And then we head into the topic of anti-something. So it can be anti-virtual machine, anti-sandbox. And we can see that nearly 4/5 do not really do anything against analysis platforms. We can see that roughly 10% for anti-VM and roughly 11% for anti-sandbox was there. and about 8% of the loaders had both options. So those were both anti-VM and anti-sandbox. The numbers here are quite low, but it doesn't prove nor disprove the claim that anti-analysis capabilities are commonly used. As this is just one loader, it shouldn't be taken as a industry standard or industry-wide figure that can be used. So the final families that dropped out of the loaders required some additional investigation because, like I said, loaders are quite often chained, and you end up digging into a lot more loaders and a lot more steps before reaching the final version. But even then, it's interesting to see that over half of all the encountered families were Agent Tesla. And we can also see that the mass logger was 15% of the total. So Agent Tesla is active in use by a lot of different actors. It's simplistic in design to a certain extent. It's not the easiest malware necessarily, but it's not the hardest to ever analyze, obviously, either. It's a commodity malware, and this suits the loader itself. This loader is not the top of the bill, hardest to ever look at, as obviously can be seen by all the nicely included symbols that make my life a bit easier. So this actually looks like a logical match as well. And there's a 5% that we called other in here, and or 15% rather. Sorry for the mix-up. 5% is mass logger and 15% is other. And the other is well, a bunch of families. Some samples only came across once, like the Mr. Fireman keylogger, which was interesting to find out which one it was. But it was only one out of more than 500. So we bundled those together. And it makes sense because generally the names that are listed here are known family names towards the industry. So when looking at the payloads, something else became clear as well. There were 513 unique loaders. However, once extracting all the payloads, there were only 447, which means we ended up with 66 duplicates. So a different loader, but it dropped the same payload. And out of these 66 duplicates, 48 were Agent Tesla. So even though the majority of the payload was Agent Tesla, even the duplicates are really Agent Tesla focused as well, which might mean that people who want to drop Agent Tesla either had easy access to this loader or preferred it for one reason or another, but there are no facts to directly support those claims. Another thing that struck me was that there were several barely utilized capabilities. The message box option was only used 7 times, but 4 times there was a message. So 3 of those just displayed an empty pop-up box. This can still be explained by the fact that the message box was only added in a later version, so not the first version. However, the remote download was used even less, and it was present from the first version that we observed. And there, one of the remote payloads, had no URL, so that's not really going to work if you try to do that. But the loader, in some way, gracefully handles exceptions by just returning the function and continuing its execution. So from a victim's perspective, it doesn't matter if such a mistake is made by the actor. So in conclusion, the loader itself is versatile. You can do quite a lot with it. It has quite some options, but the design itself is quite simplistic. So from an attacker's perspective, it's easy to use and cheap to make if you were to remake such a loader. However, it can be really impactful for organizations, which is why the onion model is recommended over the egg model to stay with those analogies. And I hope the technical analysis and also the extraction segment will help other researchers and organizations to do more research into loaders, to have a clear overview of loaders, and also to work with this. If you have any questions, you can ask them now in the chat. If you do think of a question later on that you think is worth asking, as are nearly all questions, you can reach out to me on Twitter at Libra Analysis. I will publish these slides there as well. So the hyperlinks that I mentioned are in the slides, and the blog that I wrote for McAfee's ATR team is also linked in this slide. So all the information should be in here, meaning that if you want to do something with it, then you should be able to. And with that, I will take it back to the studio.